Proofs are difficult to understand, largely because mathematicians leave out half of the steps and don't indicate what each one does. Here I'm going to give you a full 6-part Euclidean proof of a basic trigonometry fact to show you the anatomy of a proof. First, propose the task. Here we set out exactly what we mean to prove. Here what we're trying to prove is that the sides of every 30, 60, 90 triangle have these proportions. 1/2, 1, and square root of 3, which is roughly 1.732, and so on. 2. Exhibit the givens. Here we note the axioms and theorems that support our proof. Axioms are self-evident truths like 2 points suffice to define a line. Theorems are truths built up from axioms. The givens here are that we can draw an equilateral triangle. For example, draw a circle with a center and a radius, and then we sweep that radius round to form a second circle, and then we note where they intersect and make these connections. So, using the radius to circumference segment of one circle, we can create another circle, and then connecting the centers and an intersection of the two circles, which are all defined in length by the initial radius, we can very certainly make a equilateral triangle. Next, a given is that in this case, if we have an equilateral triangle, we can divide it evenly into 2 congruent triangles by dropping an altitude down. The way we can prove this, you drop an altitude by definition, the base angles reach 90, the base angles of an equilateral triangle are same sized, and if we've got two sets of same sized base angles for each of our triangles, the remaining angle in each triangle will have to be same size to bring the total up to 180 in both cases. And then finally we've got the Pythagorean theorem, a squared plus b squared equals c squared. It's not necessary to reprove all the givens or even to mention them all, depending on your audience. But in the present case, we really should at least mention the Pythagorean theorem, since that's the engine of the entire proof. Part 3 of the proof. Define what we seek. We're looking for a general way to describe the sides of the triangle so that we can view their proportions independently of any specific triangle. But this general description must take precise account of the fact that we're considering a 30, 60, 90 triangle. What we seek is always a way to describe the key term of the problem in a way that is utterly exact without sacrificing generality. Next. 4. Prepare the materials. Okay, let's take an equilateral triangle and divide it in 2 with an altitude. 2 sides have the same size, which we're going to call A, because it's an equilateral triangle, and the other side, bisected by equal triangles, we're going to call A over 2. since both of these divisions of the third side are equal in length, so each of them is half of the total, which would have been a. Oops, that should be an a over 2. Now, the base angles of each altitude are, of course, 90. And because this was originally a equilateral triangle, all of the corner angles would have been 60, 60, 60, and 60 to make up 180. And on the divided triangles, we've got a 60 and a 90, so to bring that total up to 180, we've got a 30-degree angle here and a 30-degree angle here. So now we have twice over a 30, 60, 90 triangle, two of whose sides are defined in terms of their own 30, 60, 90 proportions. Now, the size of the remaining side, we're just going to call x, because we don't know what that is. Now, we have twice over a 30, 60, 90 triangle, two of whose sides are defined in terms of their own 30, 60, 90 proportions as a and a over 2. And with a little help from Pythagoras, that's all we need to figure out what the ratio is for the remaining side. What we set up was exactly what we needed, a general way of expressing the 30, 60, 90 triangle sides. And that's what the letter A is doing for us. It's giving us a general term which is nonetheless precisely tailored to this situation. Part 5. Show how it's done. We have now a 30, 60, 90 triangle. That's 90 degrees. Let's say this is 30 and this is 60, and the proportions are a, one we don't know, and a over 2. Using the Pythagorean theorem, we'll say that the x squared plus the a over 2 squared are equal to a squared, and then x squared plus a squared over 4 are equal to a squared. And if we subtract a squared over 4 minus a squared over 4 from both sides, we get x squared is equal to 3 a squared over 4, and if we take the square root of both sides, then we get x is equal to the square root of 3a over 2. So now our triangle looks like this with its now our triangle looks like this with its sizes indicated. We've got here 1a, here we've got the square root of 3 over 2a, and here we've got a over 2. Since we're interested in every 30, 60, 90 triangle, not just this one, we can divide all the sides by a to get the pure proportions. If we do that, then we would get all the a's would disappear, and we would have this triangle. Square root of 3 over 2 whatever units, 1/2 of whatever units, and 1 of whatever units. And if we tidied things up, getting rid of the fractions by multiplying all the sides by 2, we'd end up with this triangle. That would be 2 square root of 3 and 1 for our 30, 60, 90 triangle. The final stage of the proof, 6, is called draw the conclusion. This is the point where you're entitled to editorialize a bit. It's rather barren-spirited, I think, to just stop here and say QED. This is the place where you can point out the broader relevance of the proof. For example, one could here note that the Pythagorean theorem could be similarly applied to any right triangle, for example, a 45-45-90 triangle. And this is where we get all those proportions we're always using in trigonometry.